Okay. So in the last lecture we have calculated the bending moment for flight BC. Okay. So let me know the value of the bending moment for flight BC. Okay. So flight BC bending moment. What is the value? Flight BC bending moment value. What we have calculated? Anybody? I want the values. What was the value? Everybody was absent for the last lecture. Nobody is having the data. What was the value? Let me know the value. Bending moment we have calculated, we have drawn shear force diagram. From that we have got the point of zero shear where the shear force is zero. At that point we have calculated the maximum bending moment. And I am asking you, what was the value of that maximum bending moment which we have calculated? Are you able to hear me? Yes, no? Are you able to hear me? Anybody? You can reply me in the chat also. Okay. 39.22 kilonewton meter. 39.22 kilonewton meter. Okay. So what was our depth, effective depth of the waste slab? What depth we have provided? Let me know the value of depth. What depth we have provided? Effective depth and overall depth, both the values. 180 mm. Okay, 180 mm is the effective depth. And what was the overall depth? Capital D. It is 200 mm. Right. 15 mm clear cover and half of bar diameter 10 by 2 5, so it will be 200 mm. Okay. So now we have taken the check for depth also. Now the main steel. Okay. Now the AST calculation, steel design. Now main steel for flight BC. Now for BC flight we are going to calculate the steel which is required. So our formula is AST is equal to zero point 0.5 FCKBD, 0.5 FCKBD divided by Fy in bracket 1 minus under root 1 minus 4.6 mu upon FCKBD square. This is the formula. So put the values into the formula and let me know the area of steel, AST. So if you put the values, AST is equal to 0.5, FCK is 20, B is 1000, D is 180. Okay. Here small d is there, so effective depth divided by Fy is 415 in bracket 1 minus square root of 1 minus 4.6 into mu is 39.22, it is kilonewton meter, so 10 raised to 6 Newton mm divided by FCK B D square. Put the values, let me know the value of AST, area of steel. Calculate it and let me know the answer. What is the answer? Say I don't have the calculator with me. You have to calculate it and you have to tell me the answer. This is the unsolved problem. I am not taking the solved problem. Just it is a calculation. Do it fast. $652.93. Okay. 652.94 mm square. So this is the answer. Okay. So now calculate the number of bars. So number of bars is equal to 652.94. This is the total AST divided by area of single bar. 5 by 4 into 10 we have assumed bar diameter. So calculate the number of bars. 8.31. 8.31, so nearly equal to 9 numbers. So 9 bars are there. So AST provided. Now calculate AST provided. AST provided is equal to 9 bars, each of diameter 10 mm. Okay, calculate this now. 706.86. Okay, 706.86 mm square. This area we are going to provide. Now calculate the spacing of the bars. Spacing. Okay, spacing is equal to. How do we calculate the spacing? Area of single bar divided by AST provided 706.86 into width, that is here in this case it is 1000. 1111.11. Okay, so the answer is 111.11 mm. So we will round up this spacing to 110 mm, center to center. Okay, so here we will write provide provide 10 mm bars, 10 mm diameter bars about 110 mm center to center. Okay, so this is your main steel. हे तुमचं काय main steel. This is main steel. Okay. And now for top extra bars, we just double the spacing. So here we can write provide 10 mm dia bars about 220 mm center to center. These are our top extra bars, which will be extended up to the development length. Top extra bars. Okay. So these are top extra bars. Now all this is for flight BC. All this whatever we have done, this is for flight BC. Now we will move further for flight AB. So flight AB. Okay. Now if I draw the sketch diagram for flight AB, if I draw the diagram, then it will be, this is the flight, these are the supports at A and B. A, B. Okay. So these are the points A and B. Now there is a load of, what is the UDL? What was the value of UDL which we have calculated? UDL on going length. What was the value of load, total load we have calculated earlier? I am not asking about load on landing. Let me know the total UDL we have calculated, which we have calculated. 20.56. Okay. So up to the length of 2.2 meter. Okay. From here, this is 20.56 kilonewton per meter. And for the next, this is landing part is there. So what was the load on landing? We have calculated already. 5. Okay, it is 5 kilonewton per meter. And now the length, this is 1.7, 1.5 plus zero point 0.2 of the support. And here at this side, it is 2.2. So this is 2.2 meter and this is 1.7 meter. You can refer the diagram which is already there with you. Okay, you can refer the diagram. So now again, there is no direct formula for this type of beam to calculate bending moment. Okay, so we will project these lines so that we can calculate SFD and BMD. Okay. So now let the reaction at point A, here it is RA. This reaction is RA. Here the reaction is RB. This is our baseline. Okay. First we will draw SFD, and where we get the point of zero shear. At that point we will calculate the bending moment, because bending moment is maximum where the shear force is 0. Okay. So now here first we need to calculate the reactions. Now if you see the beam, this is not a symmetrical beam, so we have to calculate RA and RB separately. So now I will take summation M about B is equal to 0. Clockwise moments are positive, anti-clockwise moments are negative. Okay. So now you take the moment. First thing is RA into how much it is, 2.2 plus 1.7, it is 3.9. 3.9. RA is moving up, so it will rotate in clockwise direction, so this is plus. Then this UDL, first of all convert this UDL into the point load. So area of that rectangle, area of rectangle 20.56 into 2.2. Okay, this is nothing but conversion of UDL into the point load. Now the distance, now this converted load, this converted force will act at the center of this UDL. Center means what? If this total is 2.2, then it will act at a distance of 1.1 from this end. 1.1 from this end, and where we are going to take the moment at point B. So from point B it is 1.7 plus 1.1. Okay, so 1.7 plus 1.1, it is 2.8. It is 2.8 and it is moving down, so it is minus. It is moving down, so it is minus. Next, again minus this UDL of 5 kilonewton. It is again area of rectangle 5 into 1.7 conversion of UDL into the point load, and it will act at the center of this, so 1.7 by 2, which is the same distance from point B. All this must be equal to 0. So therefore RA is equal to, find out the value of RA. 34.32. Okay, 34.32 kilonewton. We have got the positive answer. So RA is moving up, direction is not going to change as we have got the positive answer. Now apply summation Fy equal to 0. Summation Fy equal to 0. Upward forces positive, downward forces negative. So RA is moving up, so plus RA minus this load 20.56. So it is 20.56 into 2.2. Okay, so this is the point load minus 5 into 1.7. Okay, plus RP is equal to 0. Therefore put the value of RA and let me know the value of RP. 19.37, 19.37 kilonewton. This is the value of RB. Now we will draw the shear force diagram directly. Okay, so just be ready with your calculator only. Only the calculator is required. So always we start from left to right. So our left hand point is A. So at A the force is upward. Remember the thumb for shear force. If the force or the reaction is moving up, then you should consider it as a positive. If the force or reaction is moving down, then you should consider it as a negative. So at point exactly at point A there is a reaction RA which is moving up, so it is positive. And what is the value? It is 34.32. So I will plot that over here. This is the line. Okay. Now on your calculator type plus 34.32. Okay, type plus 31.32 and press equal to. Press equal to. Okay. Now next values you are going to tell me, so that is why I am telling you. Take the calculator and on that calculator type plus 34.32 equal to. Okay. Then next, as we left the point A and move towards the point, suppose now this is new intermediate point, this is point C. So from A to point C, okay, if required, we will project down this point C also. This point C also we will project it over here. Okay. So now in between A to C, there is a UDL. So there is a rectangular loop. Okay, which is moving up or down? It is moving down. So it is minus. Okay, and convert that UDL into the point load. So 20.56 into 2.2. What is the answer? What is the answer? $45.23. What is the answer? No, no, 45.23. How it is possible? Minus 10.91. Okay, that is the correct answer. Minus 10.91. So we will take it down over here. This is minus 10.91. This point. Okay, this is 10.91. And after that, now again, as we leave the point C, there is again UDL in between C to B. Okay, and it is also moving down. So down means minus. Again, convert the UDL into the point load. 5 into 1.7. So it is 19.41. From this point, it is here. 19.41, and exactly at point B reaction RB is there, which value is 19.37, so it will become 0. Okay, here it will become 0. So it is 19.37 kilonewton. This is your SFD in kilonewton meter. This is 19.37. This is 10.91. And this is 34.30. All these are in kilonewton. Now see, here is the point of zero shear. This is called as point of zero shear. Okay. So this point we want to calculate, because at this point our bending moment is maximum. Our bending moment will be maximum. Okay. So see these two triangles. This is the one triangle and this triangle is the second triangle. This small triangle is the second triangle and this big triangle is one triangle. So here these two triangles are the similar triangles. By which test? By AA test. These two triangles are the similar triangles. This angle is 90 degree, this angle is also 90 degree, and these two angles are same as they are opposite angles. These two triangles are similar by AA test. Okay. Then suppose now I will assume, suppose this distance as x from C point up to this point of contraflexure. Okay. Let us assume that this is x, this distance is x. So if this is x, then this total is 2.2, out of which this is x. Then this remaining will be how much? This remaining distance, it is it is 2.2 minus x. Okay, it is 2.2 minus x. Now we know that similar triangles are having their sides in proportion. Okay, so the ratio of height to base we will take. So 34.32 first side. So here 34.32 divided by 2.2 minus x, which must be equal to, okay, so this is 34.32, this is height, this side, ratio of this side to this side must be equal to ratio of this side, that is height to x. So it is must be equal to 10.91 by x. So it is equal to 10.91 by x. So solve it, so you will get the value of x. If you solve, we will get the value of x, and x is measured from point C. Let me know the value of x. Point 53. Okay. So x is equal to 0.53 meter. So from where we got this value? This value is from this side. From point C, it is 0.53. Okay. So from point A, if I want to calculate it from point A, so what will be the value? If I want to calculate it from point A, it will be 2.2 minus 0.53. What is the answer? 2.2 minus 0.53. 1.67. Okay, this is 1.67 meter. Now at a distance of 1.67 meter from point A, at this point we will get the maximum bending moment. Okay, so here I will write bending moment at 1.67 meter. So that is our maximum bending moment. So it will be at this point. So it is Ra into 1.67. Ra is moving up, so positive. Ra is 34.32. 32 or 22? 32 into 1.67 minus this UDL. Okay, this UDL we need to consider, but up to this point here. So what is the span of the UDL now? It is 1.67 meter because this is 1.67. Okay. So, and what is the distance? 1.67. So its CG will be at a distance of center of 1.67. Okay. So here it will be 20.56 into 1.67. This is conversion of UDL into the point load. Plus how much is the distance? What is the distance? So here it is 1.67. Here somewhere the section is there. It will be at the center of 1.67. So it is 1.67 by 2. So it is 1.67 by 2. Okay. So what is the maximum bending moment? 28.64. Okay. So this is the bending moment for flight AB, maximum bending moment, and for flight BC it is 39. Okay, 39.22. So there is no, again there is no need to take the check for depth, as we have already taken it for the higher bending moment than this. Okay. So now steel calculation. Again main steel. So our formula of AST I will write over here. Now put the values in this formula and let me know the value of AST. Okay, so put the values. AST is equal to zero point 0.5 FCK B D divided by FY in bracket 1 minus square root of 1 minus 4.6. What was the bending moment we have calculated? 28.64 into 10 raised to 6 whole divided by FCK B D square. Therefore, AST is equal to, if you solve this, you will get the value of AST as 465.94 465.94 mm square. This is the value of AST. Calculate number of bars. 465.94 divided by 5 by 4 into 10 square. 10 mm is our bar diameter. So what is the answer? 5.9. Okay, 5.9. So nearly equal to 6 numbers. So calculate AST provided. 6 into 5 by 4 into 10 square. 471.24. 471.24 mm square. So this is the AST provided. Okay. So now we know the AST provided. So calculate the spacing. Calculate the spacing. Spacing S is equal to area of single bar divided by AST provided 471.24 into width. Let me know the answer. 166.67. So round this value to 165 mm. So here we can write now provide 10 mm diameter bar about 165 mm center to center. Okay, so this is our main steel. This is main steel. And now top extra bars we need to provide. So here we can write provide 10 mm bar about 165. So just double this spacing, 230 mm center to center. So these are our top extra bars. These are top extra bars. Okay, so this is the main steel for flight AB. BC साठी काय आले तुमचं for BC 10 mm bars about 110 mm center to center main bar and top extra bar is 220 mm center to center 10 mm diameter. For flight AB your main steel is 10 mm bar about 165 mm center to center. Okay, and top extra bar is 10 mm about 230 mm center to center. This is for BC and AB. Now distribution steel for both the flights. Okay, so we will calculate the distribution steel now. Here I will write distribution steel for flight for flights AB and BC. Distribution steel will be same because it is given in the percentage, so it will be same. So for Fe415 it is 0.12% of gross area of cross section. Okay, so ASTD distribution steel, AST distribution is equal to 0.12%, so 0.12 divided by 100 multiplied by B into D. Therefore ASTD is equal to 0.12 by 100 into B is 1000 into D is 200. It is 240. This is 240 mm square. So assume 8 mm diameter bar for distribution steel. Okay. So here I will say assume 8 mm diameter bar for distribution steel. In the last lecture I have told you how to take the spacing of top extra bar. Okay, you can see that video I have already uploaded on the link, and for your kind information that is the thumb rule for the top extra bar. Whatever is the spacing of your main steel bars, just double the spacing of top extra bar. Okay, because for every alternate main steel bar we need to provide the top extra bar in the staircase. So that is why whatever may be the spacing of your main steel bar, you have to double the spacing for top extra bars. In total staircase, your top extra bar should be half number of bars. Your top extra bars must be half of that of total main steel bars. Okay, so that is the thing behind this. So assume 8 mm diameter bars for distribution steel. So here number of bars is equal to, it is 240 divided by 5 by 4 into 8 square. How much it is? It is 4.7. Okay, so this is 4.7. So we will really round up to these 5 numbers. Okay, so distribution steel provided. What we are going to provide? We are going to provide 5 bars, each of diameter 8. Calculate now. It is 251.32. Okay, 251.32 mm square. This we are going to provide. So now calculate the spacing of distribution steel. Spacing. Spacing of distribution steel. It is area of single bar. Area of single bar divided by AST provided multiplied by width. 200. Okay, this is 200 mm center to center. So here we can write provide 8 mm diameter bars about 200 mm center to center. Okay, so this is our distribution steel. This is our distribution steel. Okay, so now the last part of the numerical is remaining, that is the reinforcement detail. Okay, so we will draw the reinforcement details for both the flights. We will draw the sectional elevation. Okay, so sectional elevation we will draw. So you can copy me. I will start drawing. This is the staircase. This is now flight BC. Okay, flight BC and AB both we will draw the reinforcement details. So this is flight BC. Now we are drawing for flight BC. Okay, reinforcement details. So first of all, main steel, main bar. Okay. So main steel bar, it will start from here, then it will move like this. From here it is bent, It is going up from this side. Okay, this red is your main steel. In flight, we are talking about flight BC up to the clear cover, and then it is again moving down for the anchorage purpose. Okay, this is your main steel bar. This is the main steel bar. I can say this bar is, this is about 10 mm diameter, about 110 mm center to center. This is my main bar. Okay, then we will draw the top extra bars. So top extra bars, first top extra bar will start from this point. The top extra bars like this, and it will anchored over here inside this bar, and from this it will move down up to the development length. Okay, you have to calculate the development length. To here. This is your top extra bar. This bar is of, this is of 10 mm diameter, about just double the spacing of main steel, 220 mm center to center. Okay, similar top extra bar is there at this landing also here. So it will start from this point, then it will move up to here, this point, straight line, and then again it is bent up. This is also the top extra bar. And last, that is your distribution steel. That distribution steel now I will draw here. All these are the distribution steels, these bars. So all these are the distribution steels. So this steel is 8 mm bars, 8 mm diameter bars, about, what is the spacing? Spacing of distribution steel, just we have calculated, this 200 mm. 200 mm center to center. Okay, so this is the reinforcement details for flight BC. Okay, similarly we can draw the reinforcement details for flight AB also. For flight AB also we can draw the reinforcement details. Now we will draw it. Similar diagram we are going to draw. Just we are going to place the reinforcement of the respective flight in as we have calculated. Okay, so now again the main reinforcement. I will draw here the main reinforcement. So this bar will start from here. Here also you can copy down this. Okay, and then from here it will move down like this. Okay, so there is a gap. That gap is the clear cover which we left. So this steel it is. This is again 10 diameter bar, about, for this I think 165 center to center, and this is we are drawing for flight. This is for flight AB. Okay, so this is your main steel. Then we will draw top extra bars. So first top extra bar, it will be like this. Okay, so this is the top extra bar. Now this bar will be anchored over here. Then again okay, so these two are the top extra bars. So we know the top extra bar, it is 10 diameter, about 230 center to center. And last distribution steel, that we will draw over here, distribution steel. This is the distribution steel. Okay, and now we will give name to this also. This distribution steel, it is 8 bar, about 200 center to center. These are your 8 bars, about 200 center to center. Okay. So these are the reinforcement details of your open well staircase for flight AB and flight BC. So these are the only two varieties of problem in your unit number 1. So actually with these two examples, your unit number 1 is over here actually, but still today the time is there, so we will take one example, another example, and you try to solve it. Okay, so is it over? Shall we move to the next example? I will give you 2 minutes. Please draw the diagram. And once it is over, let me know. Shall we move further? Is it over? So we will take the next problem. Design the dog-legged staircase. Design the dog-legged staircase for for public building for a public building having 3 meter width 3 meter width of stairs, comma 1 meter approach 1 meter approach and 200 mm wall support from all sides. Stop. Okay. From all sides. The live load the live load on stairs is 4 kilonewton per meter square. Full stop. Use M20 and Fe415. Use M20 and Fe415. This is the given problem. Read it and let me know what you will do. First read it, then try to draw the sketch what is given so that it will get cleared. Take the floor to floor height as 3.6 meter. Take floor to floor height 3.6 meter. Okay. So here first what we will calculate? We will calculate height of single flight, which is equal to 3.6 is total floor to floor height divided by 2, so it is 1.8 meter. Okay. Then assume riser and trade. So assume riser R is equal to assume riser R is equal to 150 mm and trade is equal to 250 mm. Okay. This is what I have assumed, 150 and 250. Okay. 250 is little bit on shorter side. You can also go for 300 also. Okay. So instead of 250 now, you will go for 300. It will be sufficient to keep your foot on it. Okay. So 300 mm. So now number of risers. Calculate number of risers. Number of risers in a single flight, which is equal to 1800, that is height of single flight, divided by 150, divided by 150. So how much it is? It is 12. Okay, so it is 12 numbers. Okay. Now number of trades. Number of trades. So number of trades is equal to number of risers minus 1. So 12 minus 1, which is equal to 11 numbers. 11 numbers. Okay. Now 11 trades are there in a single flight. So what we have assumed, 300 mm is the uh, length of each trade. So from this we can calculate the going length. So going length is equal to, how many trades are there? 11. 11 into 300, which is equal to 3300 mm is the going length, which is equal to 3.3 meter. Okay. So now if I roughly draw the sketch, okay. So this is 1 meter, that is your approach slab. Then this is the dog ladder staircase which I have drawn in plan. This is 1 meter up to this point from here. From this point here up to here. This is your going length. This is your going length. So this is 3.3 meter. Okay. And assume this is the landing. Assume the landing as 1.2 meter. Assume the landing as 1.2 meter. Okay. And there is a wall which is surrounded from all four sides. So there is a wall. Okay. This is the wall. Okay. And the thickness of this wall, this thickness, how much it is given? The thickness, it is 200 mm thick. This is 200. Width of support is 200 mm. Now if you draw the staircase, these are your threads. I am drawing it over here randomly. For single flight only I will draw. For next flight you can imagine how it will be. Okay. So this is the overall total, and approach slab will be here up to this point. It's here. Okay. And this wall should be dotted. This side wall should be dotted. If the support is there, then it is resting on the surface. Okay. Or otherwise for this side now. Okay, let it be. So this is your approach and this is landing. This is your typical staircase plan. And if you calculate the effective length, then that effective length will be center to center distance between the support. So this is the center and this is also center of the support. And now whatever may be this length, this is your effective length. This is your effective length, and this length will be here L effective. If you calculate, then it is from left side it is 0.2 plus your approach is 1 plus going length is 3.3 plus landing is 1.2 and plus 0. So if you do all this calculation, then you will get the value of L effective. Okay, 0.2 by 2, correct. Here, see, L effective, that is what we were talking about. So L effective is equal to, see, the width of support is 0.2. Okay, so from the center of the width of support, so it should be 0.2 by 2 plus 1 plus 3.3 plus landing is 1.2 plus again supporting wall is there 0.2 by 2. So if you solve this, you will get the effective length. Let me know the value. 5.7. Okay, it is 5.7 meter. So now this is the effective. Now we will calculate the depth. So here you can write assuming depth of west slab, depth of west slab as 40 mm per meter of effective span. Okay. So therefore, capital D overall depth is equal to 40 mm into 5.7. असिस्टंट एचओडी आहेत ते सध्याला. So what is the value? D 40 into 5.7. 228. Okay, 228 mm. So we will round up this value to 230 mm. So this is our overall depth. Okay. Now similarly here I can write assume 15 mm clear cover and 10 mm bar diameter. Effective depth small d is equal to your overall depth minus clear cover minus half of bar diameter. So it is 210 mm. Okay, it is 210 mm. Now the next thing is loading calculation. Next is the load calculation. So load calculation. So we will calculate all the load now. First, dead load of west slab. Okay. So dead load or weight of west slab. Both are the same thing. What is the formula for this? If I write the formula, then the formula will be D into 25 into under root r square plus t square divided by t. This r square plus t square by t is, this term is for that angle theta sec theta, because this is the inclined slab. Now if you put the value, d is, it is 0.23 multiplied by 25 into under root r square 0.15 square plus 0.3 square divided by t 0.3. So what is the answer? 6.43. Okay, so this is 6.43 kilonewton per meter. Okay. Then weight of steps or dead load of steps is equal to, formula is r by 2 into 25, which is equal to r is 0.15 by 2 into 25. What is the answer? 1.875 kilonewton per meter. Okay. Then floor finish is not given. So floor finish, which is equal to, so here we will assume 1 kilonewton per meter square. Here we will assume as 1 kilonewton per meter square. Okay, so it will be 1 into 1, which is 1 kilonewton per meter, because per meter length we are calculating everything. 1 meter width of stair is considered. Okay, 1 into 1. So now floor, all this part is over. Now live load is equal to, it is how much it is given. Live load. So what is live load? What is given? It is 4 kilonewton per meter square. So it is 4 into 1, which is 4 kilonewton per meter. 1 is the width of the stair. Okay, so it is 4. Now total load. So add all these things. So you will get the total load. Total load is equal to, let me know the value of the total load. 6.43 plus 1.875 plus 1 plus 4. So this will be your total load. 13.30. 13.30 kilonewton per meter. Now calculate ultimate load. So ultimate load is equal to 1.5 into 13.30. 19.95. Okay. So it is 19.95 kilonewton per meter. Okay. Now you know the load, you know the effective length, calculate the bending moment. So bending moment, bending moment. So we are going to calculate the bending moment now. So bending moment is equal to WL square by 8, as it is dog-legged staircase. W is 19.95, L is effective length is 5.7 square, whole divided by 8. Let me know the answer. 81.02. Okay, so 81.02 kilonewton meter. 81.02 kilonewton meter. This is the answer. Check the calculation for each and every step. Please do the cross check. Okay. Now once you calculate the bending moment, the next is the check for depth. Check for depth. Whatever depth we have provided, is it sufficient or not? That we are going to check. Okay. So how we are going to check that? We will equate bending moment to moment of resistance. So equate bending moment to moment of resistance. Here, what is the value of bending moment? It is 81.02 into 10 raised to 6, which is equal to 0.138 FCK B D square. Here your D is D required. So again it is 0.81.02 into 10 to the power 6. 0.138 FCK is 20. B is 1000 into D required square. So therefore D required is equal to 171.33. So required depth is 171.33 mm. So here D required, which is equal to 171.33 mm, is less than D provided, which is equal to 210 mm. Hence this is safe. This is safe. Okay. Now once you came to know that this is safe, after the check for depth, what we do in dog-legged staircase? Steel calculation. Okay. We will design the reinforcement. So next is the steel reinforcement. Okay. So steel reinforcement, you know the formula. AST is equal to 0.5 FCKBD upon Fy under root 1 minus under root 1 minus 4.6 mu upon FCKBD square. Just put the value, you know the bending moment. So if you put the value, then AST is equal to 0.5 into FCK into B into D whole divided by Fy in bracket 1 minus square root 1 minus 4.6 into mu 81.02 into 10 raised to 6 whole divided by FCK B D square. So therefore area of steel AST is equal to calculate the answer now. 1214.97 mm square. 1214.97 mm square. Okay. 1214.97 mm square. So now calculate the number of bars. Number of bars. We have assumed 10 mm bar diameter. So number of bars is equal to 1214.97 divided by 5 by 4 into 10 square. What is the answer? 15.46. So which is round it up to 16 numbers. Okay. So calculate the AST provided, which is actually provided. AST provided. What we are going to provide? We are going to provide 16 bars, each of diameter 10. 1256.64. 1256.64 mm square. Okay, so this is the AST provided. Now calculate the spacing. Spacing is equal to area of single bar divided by 1256.64 into width. Okay. Calculate this answer. Ah, 62.5 mm. Okay, so it is 62.5 mm. So we will round this up to 60 mm. Center to center. Okay, 60 mm center to center. So this is the spacing. So finally we can write provide 10 mm diameter bars about 60 mm center to center. So this is your main steel. This is your main steel. And then now top extra bars. So provide 10 mm diameter about double the spacing 180 mm center to center. These are the top extra bars. Top extra bars. Okay. Then now this is our main reinforcement. After that now distribution steel. So ASTD distribution steel. Now Fe415 is there. So it is 0.12% of gross area. 0.12% of gross area. So it is 0.12 by 100 into gross area B is 1000 into area 230. So ASTD is equal to, so which is equal to 276. Okay. Calculate number of bars. 276 mm square. So number of bars. So before that, you write down assume 8 mm bar diameter. For distribution steel, we take the bar diameter generally 8 mm. So you write that sentence. Assume 8 mm diameter bar, and then write this step. 5.5. Okay. So 5.5 which is equal to 6 numbers. So calculate AST distribution still provided which is equal to 6 into 5 by 4 into 8 square. Three zero 1.6 which is nearly sorry 301.6 mm square. This is the area which we have provided. Now calculate the spacing. Area of single bar divided by 301.6 AST provided into width. 166.67 which is nearly equal to 165 mm center to center. So here I can write provide 8 mm diameter bars about 165 mm center to center. So this is your distribution. Okay. Now the reinforcement details you can draw it by yourself also. This is the homework for you. Draw the reinforcement details of this staircase. Okay. I will write here homework. Draw reinforcement details. Just you need to draw the details. Okay. So for today we will stop over here.